Hello, good afternoon everyone. Today I am going to lecture on the topic of Introduction to Fluid Mechanics. Myself, Kausik Bera. Now I am pursuing PhD from NIT Silchar. So today's topics of discussion, this is the first module of our curriculum, Properties of Fluids. So basically there are in this module fluid definition, distinction between the solid and fluid, units and dimension, properties of fluids, density, specific weight, specific volume, specific gravity, viscosity, compressibility, vapor pressure, capillarity and surface tension. So at first we should know what are the application of fluid mechanics, and basically in application of in different wings as per civil engineering and mechanical engineering. So this is the application where we can use to design the dams, spillways, hydraulic jump, to design water, oil and gas pipeline network, to study the oceanography and coastal engineering, to study the water and air pollution, to design slabs that resist to water and groundwater pressure, to design the bridges across the river, to design the inshore civil engineering infrastructure. And there are lots of uses of fluid mechanics in the various different field of engineering. As civil engineering, it may be in fluid mechanics, it may be in mechanical engineering and aerodynamics everywhere. So we should first know what is fluid. So fluid mechanics is the branch of science deals with behavior of fluids as well liquids or gases at rest as well as motion. The term fluid used to denote matter in liquid or gaseous phase as opposed to a solid. A fluid will undergo continuous deformation when subjected to shearing forces, and deformation will continue so long as the shearing forces continue to act on the fluid body. So fluid is a substance in the liquid or in gas phase. A solid can resist an applied shear stress by deforming. A fluid deforms continuously under the influence of a shear stress, no matter how small. In solid, the stress is proportional to strain, but in the fluids, stress is proportional to strain rate. When a continuous shear force is applied, a solid eventually stops deforming at some fixed strain angle, whereas a fluid never stops deforming and approaches a constant rate of strain. Here in this diagram, this is the contact area and shear stress. This is the tau, which is F by A. The force is acting on this, and this is the deformed rubber, and here is some angle. This is called shear strain with respect to. So in this liquid or gases, there are lots of differentiate. In liquid, groups of molecules can move relative to each other, but the volume remains relatively constant because of the strong cohesion forces between the molecules. As a result, the liquid takes the shape of the container it is in, and it forms a free surface in a large container in a gravitational field. A gas expands until it encounters the walls of the container and fills the entire available space. This is because the gas molecules are widely spaced and the cohesive force between them are very small. Unlike liquids, a gas in an open container cannot form in a free surface. This is the example of a liquid where fully occupied at a certain level, there is some free surface, but gas there is fully occupied. Because of the cohesion of the intermolecular bond, so this shape changes and its form also changes. So what is the basic differences between liquid and gases? So liquid difficult to compress and often regarded as incompressible, and gases easily to compress, changes volume in large and cannot normally be neglected and are related to temperature. occupies in liquid occupies a fixed volume and will take the shape of the container, and no fixed volume for gas. It changes the volume to expand to fill the contained vessels. If for liquid, a free surface is formed if the volume of container is greater than the liquid, but in gases completely fill the vessel so that no free surface is formed. So this is the diagram where we can define the solid, liquid and gases. There is the form of different. Intermolecular bonds are strongest in solid and weakest in gases. So the molecule in a solid are arranged in a pattern that is repeated throughout. This is the molecule bonding structure. And for liquid, this one the liquid. In liquid, the molecule can rotate and translate freely. But for the gases, in the gas phase, the molecules are far apart from each other and molecular ordering non-existence. So gas and vapor are often used as synonyms words. So gas, what is the difference between the gas and vapor? So in gas, the vapor phase of a substance is customarily called a gas when it is above the critical temperature. But vapor usually implies that the current phase is not far from a state of condensation. So these are the changes. Though this is the approaches, microscopic approaches and statistical approaches. So where you can define the classical approach, we can say microscopic or microscopic or classical approach does not require a knowledge of the behavior of individual molecule and provide a direct and easy way to analysis engineering. And microscopic or statistical approach based on the average behavior of large group individual molecules. So these are the application areas of fluid mechanics. So fluid dynamics, here we applied natural flow and whether this power plant we can use this of for boat, aircraft and airspace, human body and cars, we can use this the fluid mechanics as an engineering tool. This is the wind turbine, piping and plumbing system. This is the industrial application. So basically a history of fluid mechanics where very years ago, we can say in the British era 1800, 1900s at that time. So we can use the pipeline, each clay pipe. This is uses of a clay pipeline and a mine hoist power the reversible water wheel. So this is the application already we have done in 1800, 1900 years ago. So this is the Reynolds, where this is the instrument, or this is the pipe of turbulent pipe instrument demonstrating the onset of a turbulence pipe being operated at University of Manchester in 1975. This is the Wright brother take flight, and this is the turbine where this is the application of fluid mechanics. So classification of fluid flows, there are lots of classification. So basic to viscous and inviscid region of a flow. Viscous flow, what is viscous flow? So flow in which the frictional effect are significant. So inviscid flow region, in many flow of the practical interest, there are regions where viscous forces are negligibly small compared to the internal and or Forcer forces. So this is the inviscid flow region, this is viscous flow, and this is the inviscid flow region. And external flow and internal flow, this is also the different type of flow. The external flow, the flow of a unbounded fluid over a surface such as a plate, a wire or a pipe. And internal flow, the flow in a pipe or a duct if the fluid is comparatively bounded by the solid surface. So this is the external flow over a tennis ball and the turbulent wake region behind. And another type is compressible versus incompressible flow. This is important very. Incompressible flow, if the density of the flowing fluid remains nearly constant throughout, this is called incompressible fluid. And compressible fluid or compressible flow, if the density of a fluid changes during flow, so high speed gas flow, it can say that this is the compressible flow. Laminar flow and turbulent flow. So this is the picture of a laminar flow, this is transitional and this is turbulent, where the laminar flow is the highly ordered fluid motion characterized by the smooth layer of fluid, the flow of high viscosity fluid such as a oil and at low velocity is typically laminar. And turbulent flow, so the highly ordered fluid motion that typically occurs at high velocity and characterized by velocity flocculation, the flow of low viscosity fluids such as air at high velocities is typically turbulent. Transitional flow, in between two stage and laminar flow and turbulent flow, this is called transitional flow, a flow that alternates between being laminar and turbulent. Here is the three diagrams. This is the diagram of a laminar flow, this is the transitional, after that this is a turbulent flow. So, and this is the natural, or you can say unforced versus forced flow. So forced flow, at the name you can define this: a fluid is forced to flow over a surface or in a pipe by external means such as pump or a fan. And natural flow, fluid motion is due to natural means such as the buoyancy effect, which is manifest itself as the rises of warmer and fluid and the fall of cooler. So it can example of a natural flow. So steady flow and unsteady flow. So these are the examples of a steady flow and unsteady flow. So this is the steady flow. The term steady implies no changes at a point with time. You can say that at a rest condition. And unsteady flow, the opposite of the steady is unsteady. So the term uniform implies no changes with location over a specified region. The term periodic refers to the kind of unsteady flow in which the flow oscillates about a steady mean. Many devices such as turbines, compressor, boiler and heat exchanger operate for long period of time under the same condition, and they classified as a steady flow device. So these are the unsteady flow example. This is a unsteady flow. This is long exposure picture of a same flow, unsteady flow. These are the example. So another types of flow is 1, 2 and 3 dimensional flow. So by naming we can understand that if the flow is said to be 1, 2 or 3 dimensional, if the flow velocity varies in 1, 2 or 3 dimensional respectively. So the variation of the velocity is certain direction can be small relative to the variation in other direction and can be ignored. So now we discussed about the different type of flow. Now we will learn what are the different type of properties of fluids. So basic properties just like pressure, temperature, volume, mass, these are the basic property. And other properties like viscosity, thermal conductivity, modulus of elasticity, thermal expansion of coefficient, elastic resistivity, even velocity and elevation. Properties are considered to be either intensive or extensive. Intensive properties means are those that are independent of mass of a system, such as temperature, pressure and density. And extensive properties are those whose values depend on the size, extent of system. Total mass, total volume, total momentum are the example of extensive property. So now an easy way to determine the property is intensive or extensive is to divide the system into two equal parts with an imaginary partition. So each part will have the same value of intensive property as the original system, but the half of the value of extension property. Suppose these are the M, V, T, P row. So here this will be the half extensive property, half of M, half of V, half of M, half of V, and intensive property will be the same T, pressure and density. So all of you know the basic density of a property of a fluid. So you can say the mass density. So this is mathematically mass of fluid by volume of fluid. So density or mass density of a fluid is defined the ratio of mass of a fluid to its volume. So the unit in density is SI unit kg per cubic meter, and we defined is a rho. The density of liquid may be considered as a constant, while the gases changes with the variation of pressure and temperature. Remind that. So value of density of water 1 gram per cc or 1000 kg per meter cube. For the density of most gases is proportional to the pressure and inversely proportional to the temperature. Liquid and solid cases, on the other hand, it essentially incompressible substance, and the variation of their density with the pressure is usually negligible. So now the another property is specific weight or weight density. So we can, this is the ratio in between the weight of fluid to the volume of fluid. So we can write the rho into G, where W is defined as specific weight or weight density. W equals to rho into G. And specific volume, it is the ratio of volume of fluid to the mass of fluid. So we can write is 1 by rho, and the unit is meter cube by kg. It is commonly applied to the gases. Specific gravity, this is an important thing for fluids. Specific gravity is defined as the ratio of the weight of density of a fluid to the weight of density of a standard fluid. So for liquid, weight of density of liquid or to the weight density of water. For gases, weight of density of gas, weight density of air. So the weight of density of liquid is into 1000 into 9.81 Newton per meter cube. For density of a liquid, we can say S into 1000 kg per meter cube. So there are the specific gravity of 0 degree temperature. Water will be specific gravity 1. For ice will be 0.92, air 0.0013. So for example, specific gravity of mercury is 13.6 and the density of mercury is 13.6 into 1000. Okay, so this will be the density. So now the important thing is viscosity. So this is a very important thing for a viscosity of a fluid, or maybe specific liquid or gases. So viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over the another adjacent layer of the fluid. Suppose these are the two layers here in example. These are the two layers. In between fluid is flowing. So in between two layers, the movement to the other surface it resists. So this is called in between the internal layer or in between the layer, it can resist to the motion of a fluid. So this resistance or this movement resistance is called viscosity. When two layers of a fluid at a distance dy, suppose this is the distance dy, apart from move over the different velocities, suppose say u or u plus d as shown in the figure, viscosity together relatively velocity causes a shear stress acting between the fluid layers. So this is the velocity profile, this is du, this is the movement dy, and this is the u, this is the velocity. And this viscosity basically we can write over mathematically with respect to the shear stress is tau equals to inversely proportional to du by dy. So as per mathematically, if we some constant uses, so tau equals to mu into du by dy. So this shear stress is proportional to the rate of change of velocity with respect to the y. So this is denoted the tau, this is shear strength. So this we can say tau equals to mu into du by dy. So this mu is called coefficient of viscosity, or we can say that this is the dynamic viscosity. So unit of a viscosity, SI unit is Newton second per meter square. And another thing is kinematic viscosity. So kinematic viscosity, it is defined as the ratio between dynamic viscosity and density of a fluid. It is denoted the nu, and the mathematically nu equals to viscosity by density. This is mu by rho. The SI unit is viscosity, kinematic viscosity is mu m square meter square by second. So Newton's law of a viscosity states that the shear stress on a fluid element layer is directly proportional to the rate of shear strain is constant of the proportionality is called the coefficient of viscosity. Mathematically this is the tau will be proportional to du by dy. So the lots of types of fluids are ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid. Ideal fluids which is incompressible and having no viscosity, and real fluid which possesses the viscosity as the real fluid, and Newtonian fluid which follows the Newton's law of viscosity, this is called Newtonian fluid, and which does not follow the not proportional to the rate of shear strength is known as Newtonian fluid. And this is the ideal fluid which shear stress is more than the yield value and shear stress is proportional to the rate of shear strength is known as the ideal plastic fluid. So this is the diagram, this is the graph, this is the velocity gradient, this is the shear strength. For ideal case, this is ideal solid, this is ideal plastic with respect to the increasing linearly, and non-Newtonian fluid like this, it's behave like this, some increasing and some decreasing, and Newtonian fluid is ideally inclined and this is the ideal fluid which follows the viscosity gradient. And another very important aspect of a properties of fluid, this is the surface tension and capillarity. This is very important for the practical applicability for fluid mechanics, hydraulics. A tensile force may be considered to be acting in the plane of the surface along line in the surface. In this diagram, the intensity of the molecular attraction per unit length along any line in the surface is called surface tension. So in any molecule, it can attract with the other molecule. It is visible or it can float any surface of that time. So this surface attract the molecule. This is called surface tension. The intensity of molecular attraction per unit length along any line in the surface is called surface tension. So it is denoted by the sigma, Greek letter sigma, and it is SI unit is Newton per meter. So surface tension on a liquid droplet and bubble. So we can define that is considered as this, in this diagram, half droplet and the half bubble. In this diagram, a small spherical droplet of a liquid radius r on the entire surface of the droplet, the tensile force due to the surface tension will be acting. Here the circumference force, and this is the droplet force. So pi r square into delta p, and this is around 2 pi r into sigma for this half droplet. And let the droplet is cut into the two halves. The force acting one half will be pi sigma into 2 pi r for the tensile due to the surface tension acting the circumference of the cut portion, and the pressure force on the area pi by 4 d square in this area will be delta p into pi r square. So here this is the circumference force, and in this area this is the area force or pressure, we can say that. So this should be for the droplet, we can write this two forces will be equal and opposite, so it can write 2 pi r sigma 5 to the pi r square delta p. So delta p will be the droplet pressure, so pi into p0, so this will be sigma phi by r. So for the bubble case, the same case, same phenomena, fundamental things will happen. 2 into 2 pi r into sigma into pi r square delta p bubble. For you can say that delta p will be 4 pi 4 sigma by r. So now we can discuss the capillarity. Another phenomena is important phenomena is capillarity. So capillarity is defined as a phenomenon of rise or fall of a liquid surface in a small tube relatively to the adjacent general level of a liquid when the tube is held vertically in the liquid. The rise of liquid surface is known as capillary rise, and while the fall of liquid surface is known as the capillary depression. So attraction, you can say the another word adhesion. Adhesion between the wall of the tube and the liquid molecules is strong enough to overcome the mutual attraction, that means the cohesion of the molecules, and the pull them up the wall. Hence the liquid is said to be wet the solid surfaces. So it is expressed in the term of centimeter or millimeter of a liquid. It is the value depends upon the specific weight of the liquid, diameter of the tube, and the surface tension of the liquid. So this is, you can say in this figure, this is the capillary, you can say here the weight, this is the liquid and this is the weight of this fluid is like this way. And here we can say when the capillary, when the fluid is rise to the capillary, we can say the capillary rise. When the fluid is downward, this will be the capillary fall. So consider a glass tube of a small diameter D open for the both ends and is inserted in a liquid, say water. The liquid will rise in the tube above the level of the water. So suppose this is height h. So the height of liquid h under a state of equilibrium, the weight of the liquid is height is h and balanced by the force surface of the liquid in the tube, but the force of a surface of liquid is in the tube is due to the surface tension. So we consider this is the surface tension of the liquid is sigma, and the angle of the contract between the liquid and glasses is theta. So area of the tube into height, so the total weight of the liquid of the height h, we can say that like this way. So height, so this is the weight is downward and the pressure will be the upward, so balance will be the same. So area of the tube into h into rho into g, and this will be pi by 4 d square, this is the area, and h height, and rho is density, and g is g. So acceleration, around acceleration, gravitational acceleration. So rho will be density of liquid, and vertical component of the surface tensile force is sigma into circumference into cos theta. Here if there is some angle, so this value will be this is the theta. So if the theta, so there is some force, so this angle will be cos theta. So this portion of, like we can write the sigma into circumference into cos theta. So for equilibrium, this total weight and this vertical component will be same. Here this vertical component and the total force will be the same. So vertically this force and this weight will be the same. So for equilibrium cases, otherwise it will not rest. So here we can just for equilibrium equating these things, pi by 4 d square h into rho g, and it will be sigma pi d into cos theta. So h value, the height of rise or height of capillary rise or height of capillary t, so this value is 4 sigma cos theta by rho g d. This is the very important thing. So where we can find out this h value with respect to the equation. So we can express this value h equals to 4 sigma by 4 rho into g into d. if the diameter of D is the diameter of the glass. So if theta is less than 90 degree, so this will happen. So the liquid is said to be wet, solid. However, theta is greater than 90 degree, the liquid is repelled by the solid and tries to not to wet it. Example, water wets glass but not wax. Mercury on the other hand does not wet glass. So this is the wetting this is diagram, this is the non-wetting fluid, this is the capillary rise, this is the capillary fall. So here the example of a capillary fall. So H is less than 0. So we can, this is the same fundamental phenomena, this is the fall example where the at this equilibrium condition two forces will be the same. The second force is due to the hydrostatic forces acting upward and is equal to the intensity of the pressure where a depth of H. So we can write down the P into pi by 4 d square where the equating to force, this is the upward force and downward force, sigma rho sigma pi d into cos theta will be rho g h into pi by 4 d square. So h will be force sigma cos theta by rho g d. The same thing, but theta mercury and glass's tube is 128 degree. So this is the path, and now we will discuss about the flow pattern, different type of flow pattern: streamline, path line, streak line, and timeline. Streamline, a line is a line everywhere tangent to the velocity vector to the given instant, and path line is the actual path traveled by a given fluid particles, and streak line is the locus of the particle that have earlier passed throughout the prescribed point, and timeline is a set for fluid particles that form a line at a given instant. These are the details discussion about streamline. This is the flow pattern. This is a streamline example like this way, velocity like this way, and this is the example of a streak line flow through this path. This is object, and this fluid is flow like this way. This is the streak line example. This is the streak line flow pattern. So this is a flow pattern. And dimension of unit, this is deals with the many variable, many difficulties, types of units. So dimension of measure is independent of a particular system of unit. For example, velocity may be in meters per second, miles per hours. Dimensionally, it is always L by T, L T to the power minus 1. So dimension of relevant base of units system international as per SI system are like this. Mass, length, time, temperature, and derived unit is velocity L t to the power 1, acceleration L t to the power minus 2, forces ml t to the power minus 2. So pressure, density, specific weight, relative density, velocity, energy, power, these are the dimension, and these are the unit for SI system and English system. So these are the 1 Newton, we can say the 1 meter per second square, 1 kg of a mass to the 1 meter per second square, and the Newton is F equals to ma. So we can like this dimension analysis we can define like this way. So thank you very much all of you. Thank you so much.